In the last video, I looked at some simple results of processing stream elements. I used count and summary statistics operations, which are reduction terminal operations. Reduction operations combine the contents of a stream to return a value, or they can return a collection. On this slide, I want to show you some additional terminal operations and their return types and signatures. Some of these signatures, namely the parameters, look pretty cryptic. Don't let this intimidate or overwhelm you. Hopefully you recognize many of these types, which are functional interfaces you know by now. You can see the supplier, the buy consumer, the binary operator, the buy function, and the int function in these parameters. This tells you you'll be using lambdas or method references with these operations. This is the important part of the signature, and I would recommend ignoring the generic types as you consider these. Let me show you the same set of operations without the generics in the signature. Okay, this view of each method is a little easier on the eyes and brain, I think. There is one interface I haven't talked about yet, and that's the collector, which you can see in the first collect operation. This is not a functional interface, but there are helper methods on another class called collectors with an S that provide these special types that let us create collections of any kind. I'll be covering this interface in more detail as I review these methods. Starting from the bottom and working upwards, you can see to list there. List is one of the most common types you'd put stream elements into, so Java provided a terminal operation to give us a list back. We can also get arrays of objects or arrays of types we declare using one of the two array operations. What's not so obvious when you look at the reduce and collect operations is that we can also get back maps, sets, or any other resulting type we want from those operations. In some ways, lambdas and streams are a whole new language living inside Java. You never have to use them at all. Java existed before these features were included. Once you do understand them, though, I think you'll appreciate them. Let's get started. I'm back in the Streaming Students project because there's a lot in this code to practice on. At the end of the challenge video, I left off with identifying 5 long-term students. Now I want to process these students, placing them into some kind of container type. In this case, I'll use the toList terminal operation, inserting it after the limit operation in my last pipeline. I'll put that just before the for each statement. This compiles, and you might be wondering why, because I have toList and for each in the same pipeline here. Are both of these terminal operations? Wouldn't the second one cause an exception? Let me run this code. It runs fine, and I get the 5 students printed out. This is because the last for each is not technically part of the stream pipeline at all. In fact, if you've got IntelliJ's inlay hints turned on, you can see the inlay hint after the toList operation. It tells us that at this point, we have a list of students, and it's not a stream anymore. The for each call here is a method on that list, and not a terminal operation on the stream. In this scenario, the list method provides an unmodifiable list, restricting your ability to perform further operations or chain additional methods. Instead, it's more likely you'd want to assign the result of your list to some variable, so I'll do that next. I'll set up a local variable assignment. I'll use list with student and call it long-time learners and assign it the result of the stream pipeline. I'll add a semicolon after the terminal operation to list and remove the for each statement altogether. Again, the returned list is unmodifiable, but now you have a concrete collection of elements you could pass to other methods. I can always pass this list to the constructor of a new array list or linked list if I want my own modifiable list. Let's look at the toArray operation next. First, I'll change my variable type to just var. I'll change the toList operation, making it toArray, without passing that any arguments. This compiles, but again, let's see what IntelliJ's inlay hints can tell us. I'm getting back an array of object, which is basically an untyped array. I know every object is a student in this stream, but if I want to access a student method on these array elements, I'd have to cast that to a student array. There's an overloaded version of this operation that lets us specify the type of array we want back. It takes an int function type, which means it takes an int as a parameter and then returns an instance of something else. This means I can use the parameter to create a new array of student and use that argument value as the size of the array. I'll use the variable name size as the parameter variable name in my lambda to make this really clear. I can then use this size and pass that to the array construction code. This means it goes in the square brackets when I declare a new array of student. IntelliJ is telling me there's a better way to represent this, but I wanted you to see it this way first, so it's easier to see what's happening. Now let's use IntelliJ's pop-up to change that to a method reference. This is probably the first time I've showed you an array instantiation as a method reference. It's doing exactly what I showed you in the Lambda expression. This is another example of the unbounded receiver method reference type. In this case, the unbounded receiver is the array size, and it's used in the array's specialized construction statement. Now the inlay hint is telling me I'm getting back an array of student because of this minor change. I can also use the reduce terminal operation to give me a list back. I'll copy lines 81 through 86 and paste that on line 88. I'll change the name of my variable to just learners. I'll replace the toArray operation with collect, and I'm going to pass the result of calling a method on that collector's helper class. In this case, it has a toList method also. Now IntelliJ is giving me a warning on that. If I hover over that, the message is that this can be simplified and replaced with just the stream's toList terminal operation. There's a very important difference between these two operations, between the stream's toList operation and the collect operation that takes collectors.toList as an argument. In fact, I'll add a statement after this. I'll call collections.shuffle on my learners list. Remember, this just shuffles up values in the list. Okay, now the warning disappears. That's because IntelliJ can tell I want to modify this list. The collect terminal operation returns mutable reductions, as I've demonstrated here. I can run this code without any errors. If I change that operation back to the toList call, I would get a warning on that call to shuffle, and I'd get an exception if I tried to run it. There are two versions of the collect method as I showed you on the first couple of slides. This one, that I'm showing you here, takes one argument with a type of collector. I was able to get this by calling the toList method on the collectors class. So what's a collector anyway? Let's go look at that interface. I'll pull it up in the API documentation. There are three really important things on this page I want to point out. First, the interface has three type parameters. T is the type of input elements to the reduction, so this is the type of your stream elements. A is the mutable type you want to collect elements into. This can be a single type, like a string builder, or a collection type, like list. R is the final result type of the reduction operation. The second two types are usually the same, meaning your result type is often the same type you've been accumulating elements into, but you're not limited to that. The second really important thing is that this is a mutable reduction operation. I already demonstrated this to you with the list I got back from the collect operation in my last code sample. Lastly, a collector is specified by four functions that work together to accumulate entries into a mutable result container. The supplier, accumulator, and combiner methods are the primary methods you'll be using to build a result container. There is also a less used method called the finisher that provides a way to do a final transformation on the fully combined accumulated instance created. Let's look at the abstract methods on this interface. I'll select methods, then abstract methods at the top of this page. And there they are, the four methods just discussed and one additional one. This interface means we could create our own implementations of a collector interface and implement these methods. But Java has done this work for us for most of the types we'd want to use. These are supplied as static methods on the collectors class. Additionally, rather than implement a class, there is an overloaded version of the collect method. This provides a way to specify code for the supplier, the accumulator, and the combiner. This means we can just pass Lambda expressions or method references rather than build a type that implements the collector interface. Let's look at the collectors class now. First, there's a list here of the most common usages with examples. You see there at the top is an example using the collectors.toList method I used in my own example. I'll again select the method tab at the top of the screen. There's a lot of methods here and this can seem quite overwhelming. But look at the names. They start with things like averaging, filtering, grouping by, joining, and partitioning by, to name a few. Again, this is language you'd see in data queries. You can do a lot with just a few of these in your arsenal, and that's what I'm going to show you next. I'll pick up where I left off with code in the next video, and I'll start exploring the collect and reduce operations and some of the collectors methods. See you in the next video.